Okay, let's get started. In the previous lecture yesterday, we were actually doing the sum of products and the product of sum, basically the canonical logic expressions, log forms of the truth table. Today we are going to do the same thing, basically simplifying the expression, but instead of using the SOP and POS, we are going to use kmap. It's a technique which was actually was proposed by and was named after him. His name is Karnaugh. Yeah, so standard canonical SOP and POS expressions derived from the truth table are always correct, but they are rarely minimized. We also applied theorems of Boolean algebra from lecture 6 and 7, but minimization is still a challenge. So what do? Well, we can use kmap to get these most simplified expression for any block diagram or any truth table. So kmap is a graphical tool for minimizing SOP and POS. It is designed to identify terms that can be simplified using combining theorem. So it is similar to truth table in that it graphically shows the output of a Boolean equation. Each output is placed in a separate cell of the kmap. Okay. We'll start off with this first example where we have two variables x and y, and we have the output f, and say the output for this function is going to be 0, 1, 0, 1. Okay. So for two variables, we have four possible combinations: 0, 1, 2, and 3. Okay. Before I move on to kmap, I want to drive a SOP expression. So SOP, we look at min terms, which are those which are 1. So we got these two min terms here, and the expression for that would be, so we get x bar y plus xy, correct? For the POS, we look at max terms. So we look at zeros in the truth table, which are this and this right here. And the expression for that would be x plus y, and ending with this right here, x bar dot y. Okay. I can, if I like, further do some Boolean algebra, apply some laws and rules to simplify this, taking y as a common here, and this would have x plus x bar. And then we know x plus x bar is equivalent to 1, so we will basically get y here. Okay, so these are the two expressions that we got from SOP and POS. So these are the canonical forms, right? This is what we did yesterday. We're going to move on to kmap. So for a two variable truth table, we're going to have 2 by 2 table. Okay, 2 rows and 2 column. And the way it's going to work is, you notice it's got 2 axes. One is the y-axis right here, and then you got the x-axis. On the y-axis, you're going to have your most significant bit, which is x right here. Okay. And then your least significant bit is going to go over here. The way the arrangement of these cells are that you will have a decimal 0 here, a decimal 1 here, 2, and 3. Okay. Okay. So if you look at your truth table now, for 0, 0, when x is 0, y is 0, what is your f? It's 0, right? When x is 0, y is 1, what is your f? Okay. Similarly, for 2, it's 0, and for 3, it is actually 1. Okay. In this example, this is going to be 1 here. See, I brought my white eraser today. Okay, all right. So what are we going to do here? We can do this two ways. We can either implement the SOPs or like min terms, or you can do POS and max terms. For the most part in this term, we are going to implement the min terms only. So min term would mean we are looking at ones. And how you make pair, you're always looking for a set of ones in the size of 2 to the power n. So that would mean, let me just write it down. You are looking to make pairs of ones in the size of 2 to the power n. Okay, so this would mean you can make size 1, 2, 4, 8, 16, and so on. Okay, and how you make pair, you always look at adjacent ones. Okay, remember that. Okay, so looks like if you look at cell number 1 and 3, I can make a pair out of that. Okay, x can either be 0 or 1, so we have 0 here and we have 1 here, and again y can either be 0 or 1, so you get 0 here and you have 1 here. Okay, notice if you go from left to right, 0 0 makes a code of 0, 0 1 makes a code of 1, 1 0 makes a code of 2 right here, and then 1 1 makes a code of 3. So this is how the arrangement is going to be for a 2 input variable, and I'll show you how it changes for a 3 input variable. Now because we are doing sum of products here, because we made a pair using the min terms, how is x represented when this is 0 in a min term? It's x bar, right? Correct? And this is going to be x. Similarly, y, how y is going to be represented in a min term for 0? It's going to be y bar, and this is going to be y. Okay. Now, we look for a static variable in order to drive an expression from a kmap. If you look at it, can you find anything common for this set, for this rectangle, on the y-axis? Yes. Yeah, on the y-axis. We can't really find a common between these two because it touches both of these rows, right? Whereas if you look at horizontally, we can find a common and the common is y, just like he mentioned. So it's pretty simple for us over here that we can come up with an expression, a simplified expression using kmap, that f is going to be y. Whereas we got the same expression using the SOP here, but we had to apply some Boolean algebra rules and law in order to get this y right here. Whereas for the kmap, you don't really have to do that. So it's a quicker way of getting the simplified expression. Does everybody understand this concept of kmap? We're going to do a bunch of examples today. We were talking about the sequence, like how these cells are arranged in a kmap, and they will be arranged different in a 3 variable and a 4 variable. Before we go on to that part, I want you to introduce you to the gray code. Does anybody know what gray code is? Okay, all right. Gray code is just like a binary code, but the arrangement is a little different in a way that only one bit changes from going from one level to another. So say you have AB as your inputs or bits, okay? We know we have 4 possible combinations. So we have 0, 0, 0, 1, 1, 0, and 1, 1. Okay. Now notice here when we go from this level to this level, A is 0, but 0 changes to, B changes from 0 to 1, correct? If you go from this level to this level, A, which was initially 0, changes to 1, and B, which was initially 1, changes to 0. You have 2 bits changing at the same time. So if I ask you to find a common between these 2 levels, you won't be able to find it. Whereas if you want to find the common between these 2 levels, what would that be? It's 0, right? A, which is 0, it's not changing. So there's a commonality between those 2 levels. If I move from this level to this level,
Again, we see there is a common. 1 stays as it is, but 0 changes from 0 to 1. So gray code helps us to eliminate that glitch in the binary code. And how we do that? So again, I'll take that AB. These are my two inputs. Okay, so I got 0, 0, 0, 1, and then comes 1, 1, and then 1, 0. Now you notice the first two levels, A is common between the two levels because A stays 0, right? When you move from this level to this level, what is common? B, right? B stays 1. And over here, 1 stays as it is, but this B1 changes from 1 to 0. Okay, so there's only 1 bit changing at one time in a gray code. So remember this, 1 bit changes okay, so gray code sequence only changes 1 bit, 1 binary bit as we go, changes 1 binary bit as we go from one number to the next in the sequence. Unlike binary, that means that adjacent cells will only vary by 1 bit or Boolean variable. This is what we need to organize the output of a logic function so that we may view the commonality. So this was the gray code for a 2-bit system right here. Okay, if you want to generate a gray code for a 3-bit, how it would be? Well, see, I'll show you a trick how you can make one without having to memorize it for a 3-bit. You simply take the 2-bit gray code, which is right here, so I'm just gonna 0, 0, rewrite over here, 0, 1, and then 1, 1, and then 1, 0. We are going to just create a mirror image of this code right below it. So mirror image would be 1, 0, 1, 1, 0, 1, and 0, 0, correct? Now notice I can split this into 2 halves. Okay, so here's the first half. And here's the second half. To the first half, we are going to add 0 to the left. Okay. And to the second half, we are going to add 1. Okay, so there's a 3-bit gray code for you right here. If you want to do it for a 4-bit, you do the same thing, make a mirror image of a 3-bit, split it into 2 halves, add 0 to the left to the first half, and add 1 to the second half to the left. Okay, the second example of the day. Is this a SOP or POS right here? This suggests this is a SOP, right? And these are what right here? These are all minterms, right? And minterms are those for which the output is going to be 1. So 2, let me write the decimal numbers here. 3, 4, 5, 6, and 7. Okay, 2, this is going to be 1, 3 is 1, 4 is 1, 6 is 1. Okay, and rest of the other will be 0. Okay, now because there are 3 variables in here, again the most significant bit is going to go over here, which is X right here. Okay, and then you got Y and Z will go here. Okay, Okay, this will be 0, this will be 1, this will be 0, 0, this will be 0, 1, this will be 1, 1, and this will be 1, 0. How do I get that? Let's go back and see our gray code right here. Okay, so here's my gray code. The decimal value for the first number in the sequence is going to be 0, right? So 0, 0, 0, 0 makes a code of 0. What is the next number in here? 0, 0, 1, which is a decimal code for 1. 0, 0, 1 makes a code of 1, right? Next value in the cell is going to be 0, 1, 1. 0, 1, 1. Correct? This number is 0, 1, 0, which Novi is going to be 2, right? 0, 1, 0 makes a decimal code of 2. This is going to be, and then 0, 1, 3, 2. Next one is 6, 1, 1, 0, 1, 1, 0. 6, 7. And similarly, you got 4 here, and you got 5 here. Okay, so if you look at cell number 5, 1, 0, 1 makes a code of 5. Correct? Okay, this is how the arrangement is going to be for a 3-variable kmap. Again, we will do this so many times that you will actually remember this. Okay, again, because we are doing SOP, so we are looking at minterms. So let's put the minterms in here. So 2 is 1, 3 is 1, 4 is 1, 6 is 1. Okay, all right. Remember, we have to make sure that we are covering the minterms at least once, okay? And our goal is to simplify the expression, come up with the least number of gates. So how would you pair this? You can tell me what cell numbers you would make. You can make 3 and 2, right? Do you want to make that? 3 and 2? Okay, all right. Also, there's one thing in the kmap that you can wrap around to make rectangles. So in kmap, we can wrap around on the sides or edges to make a set. Okay, for example, we can make 6 and 4 like this. Okay, is there any other set that we can make? Yes, 2 and 6. So how many of you agree making another set of 2 and 6 would make sense? It's not going to have any impact upon the functionality of your device. However, it's just going to add one extra term to your expression, and we don't want that. Unless any of this minterm is covered one time by a rectangle, you don't have to pair it up again. Okay, so the expression here is going to be what? You get f here. Okay, now I'm going to get an expression for this pair right here. What is the common on the y-axis here? Again, this is going to be x bar. This is x. Y bar, z bar, y bar, z, yz, and then yz bar. Okay, so what is the common on the y-axis for this rectangle right here? It's x bar, right? X bar. And what is the common on the x-axis here? Say it again. Y, correct. Okay, and we know what we do with the minterms, we add them, right? Plus. The next set is right here, 4 and 6. What is the common here? X. And what is the common on the x-axis? Z bar. Okay. And that is our final expression. Okay. Let's just go ahead and make a logic diagram for it also. So again, I got these X, Y, and Z here. I'm gonna need I forgot to bring my stencil, so I'm gonna do it by hand today. Okay, all right. Let's just make on one AND gate right here. And I got bubble here. So this is X bar Y, and then XZ bar, get another AND gate. Okay, so this is X, Z is going to be bar, so I need a bubble here. And these two go into an OR gate. Okay. Okay. And this is going to be my output F right here. Okay. These are the two bubbles. Okay, we can try one combination here. Maybe we can try 1 1 0. X is 1, Y is 1, Z is 0. So this would mean you get what here? This is going through a bubble, so this is 0 1 0 1 goes to an AND gate, you get 0. Here Z is 0, so this becomes 1 because there's a bubble here. X is 1 1 1 goes to an AND gate, you get 1. 0 and 1 goes to an OR gate, you get 1, right? So notice in the truth table, 1 1 0 had an output 1. Okay, so even though we have simplified the expression using kmap, it is still giving us the same functionality, right? So this is the whole point of doing this kmap. So you have SOP, POS, minterms and maxterms, then we have Boolean algebra rules and laws, and then we have kmap. From now, moving forward, you're only pretty much going to be doing kmap. Okay, shall we move on to the next example, guys? Okay, all right. It's a 4-variable kmap. So again, 0 1 2 3 4 5 6 7 8 9 10 11 12 13 and 15. The arrangement in the cell for a 4-variable is going to be 0 1 3 2 4 5 6 and 7 8 9 10 11 12 13 14 and 15. Okay, again, if you create a 4-bit gray code, and you should be able to follow the sequence, and it will make this kind of arrangement in the cells. Your two most significant bits, which are A and B, they are going to be on the y-axis, and the two most least significant bits are going to be on the x-axis. Okay, I'll just go ahead and get these labels. So 0 1 1 1 and 1 0, 0 1 1 1 and 1 0. What is the code for 15? What is the binary code for 15? Yes. I'm sorry? Yeah, this one? Yeah. Thank you. Yeah, that's right. 0 1 2 3 4 5 6 7 8 9 10 11 12 13 14. Yeah, thank you. Yeah. So what is the binary code for 15, guys? 1 1 1 1, right? Double 1 double 1. So if you look at cell 15, you got 1 1 and 1 1. Okay. So this is how it's gonna make sense. Okay. Now let's insert the min terms in there. These are again the min terms right here. Okay. So 0 is 1, 2 is 1, 4 is 1, 6 is 1, 7 is 1, 10 is 1, 14 is 1, and 15 is 1. Okay, all right. How would you pair them up? Again, I just want to mention one more thing here. There are multiple ways of combining terms. Ideally, you want to make the largest possible set to simplify. Okay, so meaning if you think you can make a set of 4 minterms, you should go with that. If you can make a set of 8, then you go for 8, not for 4. Okay, how would you pair them up in this? Come on, guys. Yes. Host column. Okay. All right. Sure. I can do this right here. What else? Good. Look for a larger set. It is okay to repeat, even though like you have covered 2, 6, 14, and 10, those minterms, they can be covered again in order to make a larger set of rectangle. Yeah, not you. Come on, guys. Yes, Sri.
You use a 7, 6, 4, 7, 6, 14.
Correct. Yeah, we would do that. Okay. What else? Does anyone think that we can make another chord? Yes. 2, 6, 0, and 4. How many of you agrees we can do that? Yeah, we can do that because remember we can wrap around and they will be considered adjacent. So we can wrap around like this. Okay. All right. So let's get an expression. F equals 2. Right. Give me an expression for the green box, for the green rectangle. What would that be? What is the common here? This 0, right? What does it represent, this 0? A bar, right? A bar. Okay. A bar. And then what is the common on the vertical axis here? 0 again, so that would be D bar. Correct? Okay. This column right here, the last column, what would be the expression for that? Obviously, you cannot find any common on the y-axis because it goes through all of those combinations, but this would be the common term, right? Which is what? This is what? CD bar, right? Plus CD bar. Now this chord on the side, in the middle, what would be the expression for that? What is the common here? D. And what is common here? C. Okay. So this is the most simplified expression that you would get for this truth table using kmap. Okay. I'll just quickly fill out this. So we had 1 here, 1 here, 4 was 1, 7 is 1, 10 is 1, 14 is 1, 15 is 1. Imagine when we were doing SOPs and POS and getting an expression, and if we didn't have this kmap, what would the expression would have looked like? You know, A bar, B bar, C bar, D bar plus A bar, B bar, C, D bar plus A bar, B, C bar, D bar plus A bar, B, C, D plus A, B, C, D bar plus A, B, C, D. And on top of it, you had to do the Boolean algebra rules and laws to simplify it. So this is a lot more simpler, right? So this is the whole point of doing the kmap, getting from here to here without compromising on the functionality. We can draw the logic diagram here. Okay, let's do that. Actually, I'll let you guys do it by yourself. Make a logic diagram and verify any sequence there.